Close your eyes and imagine holding the entire universe in your hands. Not the universe as it exists today, with its billions of galaxies and countless stars, but the universe as it was 13.8 billion years ago. You're holding something smaller than the period at the end of this sentence, smaller than an atom, smaller than anything we can measure. And yet, everything that exists today, every star, every planet, every grain of sand, every thought you've ever had was contained within that impossibly tiny point. This is where our cosmic story begins. Not with a bang, but with something far more extraordinary. The Big Bang wasn't an explosion in space. Space didn't exist yet. Time didn't exist yet. The Big Bang was the sudden appearance of space and time themselves, expanding from nothing into everything we know. Here's what's really happening in those first impossible moments. The universe doesn't just expand, it inflates faster than the speed of light. In less time than it takes light to cross the width of a proton, space itself stretches by a factor of at least 10 to the 26th power. If a marble expanded at this rate, it would become larger than our solar system in that same instant. This is cosmic inflation, and it explains why the universe looks so uniform in every direction we observe. But the universe has a surprise for us. In the first second after the Big Bang, temperatures reach 10 billion degrees Celsius. That's 600 times hotter than the core of our Sunday. At these temperatures, nothing that we would recognize as matter can exist. Instead, pure energy fills the universe, and this energy begins transforming according to rules that govern everything that will ever happen. The four fundamental forces that control all cosmic behavior, separate like rivers branching from a single source. First, gravity splits off the force that will spend the next 13.8 billion years patiently gathering matter into planets, stars, and galaxies. Then the strong nuclear force emerges, which will hold atomic nuclei together against the explosive pressure trying to tear them apart. The electromagnetic force appears next, destined to bind electrons to nuclei and create the atoms that make chemistry possible. Finally, the weak nuclear force takes its place, governing the radioactive processes that power stellar fusion and allow heavy elements to form. These aren't just abstract forces, they're the architects of reality. Every time you feel the pull of gravity, witness light from a distant star, or touch any physical object, you're experiencing the direct descendants of these primordial separations that occurred in the first fraction of a second after time began. As the universe continues expanding, it cools like a pot of soup removed from a stove. When temperatures drop to 1 billion degrees Celsius, still hot enough to vaporize any planet, something remarkable happens. The first particles of matter appear. Protons and neutrons condense from the energy soup, but they can't stay together yet. The universe is still too hot, too violent. Any atomic nucleus that tries to form gets immediately blasted apart by high-energy radiation. Then comes one of the most crucial periods in cosmic history. During the first 3 minutes, as temperatures fall below 100 million degrees Celsius, the universe becomes cool enough for the first atomic nuclei to survive. In this brief window, nuclear fusion runs wild throughout all of space. Protons and neutrons collide and stick together, creating the nuclei of hydrogen and helium that will fuel every star for the rest of cosmic time. Here's the extraordinary part. The ratio of hydrogen to helium, created in these first 3 minutes, determines the composition of the universe for billions of years to come. For every 12 hydrogen nuclei that form, 1 helium nucleus appears. This precise ratio, 75% hydrogen, 25% helium, matches exactly what we observe in the oldest stars today. It's cosmic archaeology. We can see the fingerprints of those first 3 minutes written in the composition of ancient starlight. But the universe isn't done with its surprises. For the next 380,000 years, space remains opaque to light. Free electrons scatter photons in every direction, making the universe as impenetrable as a thick fog. Then, when temperatures cool to about 3,000 degrees Celsius, hot enough to melt copper electrons, finally combine with nuclei to form the first complete atoms. This moment, called recombination, changes everything. Light can suddenly travel freely through space for the first time. The universe becomes transparent, and the cosmic microwave background radiation that we detect today begins its journey toward us. When you tune a radio between stations and hear static, roughly 1% of that noise comes from this ancient light, the afterglow of creation itself. But let's step back from these cosmic scales and consider something equally remarkable. Ancient humans, lacking telescopes or equations, gazed at the same stars that had formed from this primordial hydrogen and helium, and they dared to ask the impossible question, how did everything begin? 5,000 years ago, Mesopotamian astronomers tracked the movements of planets against the background stars with astonishing precision. They didn't know they were observing worlds orbiting the sun, but they recognized patterns. They saw that celestial events repeated in predictable cycles. The universe, they realized, operates according to discoverable rules rather than random divine whims. In ancient Greece, philosophers took this insight even further. Aristarchus proposed, 2,300 years ago, that Earth orbits the sun rather than sitting motionless at the center of creation. This required extraordinary intellectual courage. To suggest that our world moves through space challenged every human intuition and religious belief about our special place in the cosmos. Here's what these early cosmic explorers accomplished. They established that the universe can be understood through careful observation and logical reasoning. When Eratosthenes calculated Earth's circumference by measuring shadows in different cities, he proved that mathematical principles apply to cosmic scales. When Hipparchus discovered that stars change position over centuries, he revealed that even the seemingly eternal heavens evolve over time. These weren't just academic exercises. Each breakthrough required someone to risk ridicule, persecution, or worse, to challenge accepted wisdom. When Galileo turned his telescope toward Jupiter in 1609 and saw 4 moons orbiting that distant planet, he proved that Earth isn't the only center of motion in the universe. The Catholic Church forced him to recant his findings, but the universe had already revealed its secret. We live in a cosmos where worlds orbit suns, not the other way around. The connection between these ancient questions and modern cosmology runs deeper than simple curiosity. When contemporary physicists trace the universe back to its origins, they're following the same logical thread that led Greek philosophers to propose that Earth moves through space. The principles are identical: careful observation, mathematical analysis, and the courage to accept conclusions that challenge our everyday experience. Here's what modern instruments reveal about those ancient insights. The cosmic microwave background radiation carries tiny temperature variations, differences of only a few millionths of a degree that represent the seeds from which all cosmic structure grew. These microscopic fluctuations in the density of space itself became the gravitational wells that would eventually gather matter into the first stars and galaxies. We exist in a universe where the largest structures we can observe galaxy clusters spanning hundreds of millions of light-years, trace their origins back to quantum fluctuations smaller than an atom. The same uncertainty principle that prevents us from knowing both the position and momentum of a single electron simultaneously created the cosmic web of dark matter filaments, along which galaxies form, like pearls on invisible strings. This is the universe that ancient stargazers glimpsed when they first proposed that celestial phenomena follow natural laws. Every atom in your body participated in this cosmic story. The calcium in your bones formed inside dying stars. The iron in your blood was forged in supernova explosions. The hydrogen in your DNA dates back to those first 3 minutes after the Big Bang, when atomic nuclei formed for the first time. You are made of processed starlight and nuclear fire, organized by the same forces that separated in the first second after time began. When you look up at the night sky, you're not observing something separate from yourself. You're seeing the ongoing story of which you are both author and character, observer and participant. The universe that emerged from that point smaller than an atom has spent 13.8 billion years creating the conditions necessary for matter to organize itself into structures complex enough to contemplate their own origins. Stars had to form, live out their nuclear-burning lifespans, and die to create elements heavier than hydrogen and helium. Planets had to condense from the debris of stellar death. Chemistry had to become complex enough to support self-replicating molecules. Evolution had to shape these molecules into organisms capable of building telescopes and particle accelerators. The questions that kept ancient astronomers awake: how did everything begin? What controls the motions of celestial bodies? Are there deeper patterns underlying the apparent chaos of natural phenomena? Are the same questions driving cosmology today? The tools have become more sophisticated, but the fundamental human drive to understand our place in the cosmic story remains unchanged. When we trace cosmic history from the Big Bang to the present moment, we're not just recounting a sequence of events. We're mapping the chain of processes that had to unfold in precisely the right order and proportions to create a universe capable of supporting complexity, consciousness, and curiosity. The fact that we can ask these questions means the universe has succeeded in creating at least one small pocket of organized matter was capable of reflecting on its own origins. This is where our cosmic adventure truly begins, not with abstract theories or mathematical equations, but with the recognition that we are the universe developing the capacity to understand itself. Every time you wonder about the nature of reality, you're participating in the same cosmic process that separated the fundamental forces, formed the first atoms, and lit the first stars. The universe that began as a point smaller than an atom now spans at least 93 billion light-years in diameter. It contains at least 2 trillion galaxies, each hosting hundreds of billions of stars, and somewhere in this vast expanse of space and time, on a small rocky planet orbiting an ordinary yellow star, matter has organized itself into forms complex enough to trace their ancestry back to that moment when everything began. The ancient humans who first dared to ask how everything started could never have imagined the answers their questions would eventually reveal, but they established the principle that guides all scientific exploration. The universe operates according to discoverable laws, and patient observation, combined with careful reasoning, can reveal even the most hidden cosmic secrets. This principle has carried us from wondering about the movements of planets to understanding the origins of space and time themselves, and it will carry us toward even the deeper mysteries as we continue humanity's greatest adventure, the quest to comprehend the cosmos that gave us birth, and the remarkable story of how everything we know came to exist. Picture the universe, 400 million years after the Big Bang. No stars shine in the darkness, no galaxies spiral through space. The cosmos stretches empty and cold, filled only with hydrogen and helium gas drifting at temperatures just above absolute zero. This is the cosmic dark age, a period when the universe had cooled too much for the primordial fire of creation to continue, but not enough for the first stars to ignite. Here's what's really happening during these silent centuries. Gravity, the weakest of the 4 fundamental forces, begins its patient work. Unlike electromagnetic forces that can both attract and repel, or nuclear forces that operate only at microscopic distances, gravity only pulls. It never pushes, it never tires, and it never gives up. Imagine invisible hands reaching through the darkness, gathering wisps of hydrogen gas like a gardener collecting morning mist. These gravitational hands grow stronger as more matter accumulates. A small cloud of gas creates a small gravitational pull, But as that pull draws in more gas, the gravitational field intensifies. More matter creates stronger gravity, which attracts even more matter in an accelerating cycle that will reshape the universe. The universe has a surprise waiting in these growing gas clouds. As gravity compresses the hydrogen and helium, the temperature begins to rise. This seems counterintuitive. We usually think of compressed gases as getting cooler, like the expanding gas in a refrigerator. But cosmic gas clouds operate under different rules. When gravity compresses gas on astronomical scales, it converts gravitational potential energy into heat. Here's the remarkable process unfolding in the cosmic darkness. A typical gas cloud starts with a temperature of just a few degrees above absolute zero. As gravity pulls the outer edges inward, the compression heats the center. When the core temperature reaches 1000 degrees Celsius, hydrogen molecules begin breaking apart into individual atoms. When it reaches 10,000 degrees, the gas begins to glow with a faint red light, the first illumination the universe has seen since the cosmic microwave background was released. But the real transformation hasn't even begun yet. Gravity continues its relentless compression, driving core temperatures higher and higher. At 100,000 degrees Celsius, electrons get stripped away from atomic nuclei, creating a plasma of free particles. At 1,000,000 degrees, the gas becomes completely ionized, and still, gravity keeps squeezing. Then comes the moment that changes everything. When the core temperature reaches 10,000,000 degrees Celsius, 600 times hotter than the surface of our Sun, nuclear fusion ignites. Hydrogen nuclei, which have been bouncing off each other for hundreds of millions of years, suddenly have enough energy to overcome their electromagnetic repulsion and fuse together. The first star in the universe blazes to life. This isn't a gentle kindling like lighting a campfire. Nuclear fusion in stellar cores releases energy at a rate that defies human comprehension. Every second, a typical star converts 700 million tons of hydrogen into helium, destroying 4 million tons of matter and converting it into pure energy according to Einstein's famous equation. The energy from this nuclear fire races outward from the stellar core, creating the radiation pressure that prevents gravity from crushing the star completely. These first stars are nothing like our Sunday. They contain only hydrogen and helium, the two elements created in the Big Bang. Without heavier elements to help cool their cores, these primordial giants grow to enormous sizes. Many reach 100 times the mass of our Sun, burning with such ferocity that they exhaust their nuclear fuel in just a few million years. Here's what these stellar furnaces accomplish during their brief, brilliant lives. Nuclear fusion doesn't stop with converting hydrogen into helium. As the star ages and its core temperature rises, helium nuclei begin fusing into carbon. Carbon fuses into oxygen. Oxygen fuses into silicon. Silicon fuses into iron. Each fusion reaction releases energy, but each step requires higher temperatures and pressures than the last. Iron marks the end of the line. Fusing iron nuclei together absorbs energy rather than releasing it. When a massive star's core fills with iron, nuclear fusion shuts down. Without the outward pressure of radiation to balance gravity's inward pull, the core collapses in less than 1 second, creating the most violent explosion the universe can produce, a supernova. The explosion doesn't just destroy the star, it creates elements that fusion couldn't produce. In the intense heat and pressure of the supernova shockwave, iron nuclei capture neutrons and build up into all the elements heavier than iron: cobalt, nickel, copper, zinc, silver, gold, platinum, uranium. Every atom of these elements in your body was forged in the heart of an exploding star. But supernovas do something even more important for the future of the universe. They scatter these newly created elements across vast regions of space, seeding the cosmic gas clouds with the raw materials needed to build rocky planets and, eventually, living organisms. Without supernova explosions, the universe would contain only hydrogen and helium forever. There would be no carbon for organic chemistry, no oxygen for water, no iron for blood, no calcium for bones. This is stellar alchemy, the cosmic process that transforms the simplest elements into all the complexity we see around us. Stars are not just balls of burning gas. They are element factories, carefully cooking lighter nuclei into heavier ones over millions or billions of years, then distributing their products throughout space via stellar winds and explosive deaths. The universe develops a rhythm during this age of first stars. Gravity gathers gas, compression ignites fusion, nuclear fire burns bright, massive stars explode, and heavy elements spread through space to seed the next generation of star formation. This cycle will repeat for billions of years, each iteration adding more chemical complexity to the cosmos. Now let's fast forward through cosmic time to witness humanity's first glimpse of this stellar majesty. When Galileo turned his primitive telescope toward the Milky Way in 1609, he expected to see a luminous cloud. Instead, he discovered that our galaxy consists of countless individual stars, each one a distant sun burning with nuclear fire. This revelation shattered the ancient belief that celestial objects were fundamentally different from earthly matter. The stars weren't jewels embedded in a crystal sphere, or holes poked in the fabric of heaven. They were physical objects, operating according to the same natural laws that governed falling stones and flowing water on Earth. Johannes Kepler took this insight further, by discovering that planetary orbits follow precise mathematical patterns. His 3 laws of planetary motion revealed that celestial mechanics operates with clockwork precision. Planets don't wander randomly across the sky. They follow elliptical paths determined by the gravitational influence of the Sunday. Here's what made Kepler's discovery so revolutionary. For the first time in human history, someone had found mathematical equations that perfectly described the behavior of cosmic objects. The same geometry that surveyors used to measure fields could predict where Mars would appear in the night sky months or years in advance. The heavens operated according to discoverable mathematical principles. Isaac Newton unified these earthly and celestial insights when he realized that the same force pulling apples toward Earth also holds the moon in its orbit and guides planets around the Sunday. Gravity wasn't just a terrestrial phenomenon, it was a universal force shaping the structure of space itself. Newton's law of universal gravitation revealed why stars form, why planets orbit in stable patterns, and why galaxies hold together despite the tremendous speeds of their constituent stars. Every particle of matter in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegant mathematical relationship explains the grand architecture of the cosmos. Gravity pulls gas clouds together to form stars. It holds planets in orbit around those stars. It binds stars into galaxies, and galaxies into clusters. The same equation that describes an apple falling from a tree also explains why the Andromeda galaxy maintains its spiral structure across hundreds of billions of stars. But Newton's insights revealed something even more profound about the nature of stellar processes. When he calculated the gravitational forces within the Sun, he realized that something must be preventing our star from collapsing under its own enormous weight. The outward pressure balancing solar gravity had to come from an energy source more powerful than any chemical process. We now know that this energy source is nuclear fusion, the same process that lit the first stars and created all the elements heavier than hydrogen and helium. Every ray of sunlight that warms your face carries energy that originated when hydrogen nuclei fused in the Sun's core, releasing photons that spent hundreds of thousands of years bouncing around inside our star before finally escaping into space. Here's the remarkable connection between stellar processes and human existence. The calcium in your bones was created inside a dying star when silicon nuclei captured additional protons and neutrons. The iron in your hemoglobin formed during the final moments of a massive star's life, just before it exploded in a supernova. The oxygen you breathe emerged from helium fusion in stellar cores. You are not just made of star stuff, you are made of recycled star stuff. The elements in your body have been through multiple cycles of stellar birth, fusion, death, and rebirth. Some of your atoms may have formed in the first generation of stars, been scattered by supernovas, incorporated into second-generation stars, scattered again, and finally collected into the gas cloud that collapsed to form our solar system 4.6 billion years ago. This cosmic recycling program has been operating for over 13 billion years, continuously enriching the universe with heavier elements and creating the chemical complexity necessary for planets, oceans, and life. Every star that lights the night sky operates as a node in this vast network of element production and distribution. The universe that began with only hydrogen and helium now contains 94 naturally occurring elements, each one forged in stellar cores or explosive stellar deaths. This chemical evolution represents one of the most important developments in cosmic history. Without it, the universe would remain forever simple, an endless expanse of hydrogen and helium gas, with no possibility for the complex chemistry that makes planets and biology possible. When we observe distant galaxies through modern telescopes, we're witnessing this stellar alchemy in action across cosmic time. The most distant galaxies we can see formed when the universe was less than 1 billion years old, and they show the characteristic signatures of first-generation stars, massive, short-lived, and deficient in heavy elements. Closer galaxies reveal the gradual chemical enrichment that occurs as successive generations of stars live, die, and scatter their fusion products into space. Our own galaxy, the Milky Way, represents the result of this cosmic evolution. It contains stars of all ages, from ancient giants that formed when heavy elements were rare, to young stars like our Sun that condensed from gas clouds already enriched with carbon, oxygen, silicon, iron, and dozens of other elements produced by previous stellar generations. The stellar nurseries, where new stars continue forming today, regions like the Orion Nebula glow with the light of hot young stars that ignited just a few million years ago. These stellar nurseries contain the same basic ingredients as the first star-forming regions 13 billion years ago: hydrogen and helium gas compressed by gravity until nuclear fusion ignites. But they also contain something the early universe lacked: heavy elements that will allow these new stars to form planetary systems capable of supporting rocky worlds. This is the gift that stellar alchemy has given to the universe. By converting simple hydrogen into the entire periodic table of elements, stars have transformed the cosmos from a place where only gravity and electromagnetic forces could create structure into a realm where chemical bonds can build molecules, minerals, planets, and living organisms. Every star you see in the night sky is participating in this ongoing creative process, fusing lighter elements into heavier ones and preparing to distribute its products throughout space when its nuclear fuel is exhausted. The stellar fires that began in the cosmic dark age continue burning today, ensuring that the universe grows more chemically complex with each passing billion years. This stellar legacy connects directly to humanity's cosmic curiosity. The same nuclear processes that create heavy elements in stellar cores also powered the formation of our solar system, our planet, and ultimately the biological evolution that produced brains capable of contemplating stellar physics. We exist because stars learned to make the elements necessary for chemistry, and chemistry learned to make the molecules necessary for life. When ancient astronomers first wondered about the nature of stars, they were unknowingly asking about their own origins. The stellar fires they observed in the night sky were the cosmic furnaces that created the very atoms from which their bodies were built. Their curiosity about celestial phenomena was the universe beginning to understand the processes that had made their existence possible. This connection between stellar physics and human consciousness represents one of the most profound developments in the cosmic story. After 13 billion years of stellar alchemy, the universe has finally created structures complex enough to comprehend the nuclear processes that forged their constituent elements. We are stellar fusion made conscious, capable of understanding the cosmic fires that gave us birth. In 1905, a young patent clerk in Switzerland proposed something that seemed impossible. Space and time are not separate, fixed stages on which cosmic events unfold. Instead, they form a unified fabric that bends, stretches, and curves in response to matter and energy. Albert Einstein's theory of relativity didn't just change our understanding of physics. It revealed that the universe itself has an architecture more strange and beautiful than anyone had imagined. Here's what Einstein discovered about the true nature of reality. Imagine space-time as a vast rubber sheet stretched in all directions. Now, place a bowling ball in the center. The sheet curves around the ball, creating a depression that affects the entire surface. Roll a marble across this curved sheet, and it will follow a curved path around the bowling ball, even though no direct force pushes it sideways. This is exactly how gravity works in our universe. Massive objects like stars and planets curve the fabric of space-time around them. Other objects moving through this curved space follow the straightest possible paths, which we perceive as gravitational attraction. An orbiting planet isn't being pulled by an invisible force. It's traveling in a straight line through curved space-time. Einstein's equations revealed something even more remarkable. If matter and energy curve space-time, then the universe as a whole must have a shape determined by its total mass and energy content. Space-time could be curved like the surface of a sphere, curved like a saddle, or flat like an infinite plane. The geometry of the universe itself became a question that observations could answer. But Einstein's theory contained a prediction that he himself found disturbing. The equation suggested that the universe couldn't remain static. Space-time itself must be either expanding or contracting. Since no one in 1915 had any evidence for cosmic expansion, Einstein added a mathematical term, the cosmological constant, to make the universe hold still. The universe had other plans. In 1929, Edwin Hubble made the most important astronomical discovery of the 20th century. Using the new 100-inch telescope at Mount Wilson Observatory, he measured the distances to nearby galaxies and their speeds of recession from Earth. What he found transformed our understanding of cosmic reality. Every galaxy Hubble observed was moving away from us. More incredibly, the farther away a galaxy was, the faster it was receding. Galaxies 1 million light-years away moved at speeds of a few hundred kilometers per second. Galaxies 10 million light-years away raced outward at several thousand kilometers per second. The relationship between distance and recession velocity followed a precise mathematical pattern now known as Hubble's law. Here's what this discovery means for the nature of space itself. The galaxies aren't moving through space. Space itself is expanding, carrying the galaxies along like raisins in rising bread dough. As the dough expands, every raisin gets farther from every other raisin, with the most distant pairs separating fastest. This cosmic expansion provided the first direct evidence that the universe has a history. If space is expanding now, it must have been smaller in the past. Trace this expansion backward in time, and all the matter and energy in the universe converges toward a moment when everything occupied the same point, the Big Bang. Hubble's discovery vindicated Einstein's original equations and revealed that the cosmological constant had been unnecessary. The universe doesn't need an additional force to balance gravity because it's not trying to remain static. Space-time itself is dynamic, evolving according to its matter and energy content. But the expanding universe posed new questions that would take decades to answer. What drove the initial expansion? Why does space expand at the rate we observe rather than faster or slower? And what determines the ultimate fate of cosmic expansion? The answers began emerging in 1965, when two radio astronomers at Bell Labs detected a faint background of microwave radiation coming from every direction in space. Arno Penzias and Robert Wilson initially thought this signal was interference from pigeon droppings on their antenna. Instead, they had discovered the afterglow of creation itself, the cosmic microwave background radiation. This ancient light carries the fingerprints of the universe, as it existed 380,000 years after the Big Bang, when electrons first combined with nuclei to form neutral atoms. Before this moment, free electrons scattered light in all directions, making space opaque. After recombination, light could travel freely, and the universe became transparent for the first time. Here's the remarkable story this cosmic background radiation tells. The temperature variations in this ancient light differences of only a few millionths of a degree represent the seeds from which all cosmic structure grew. Regions that were slightly denser than average had slightly stronger gravitational fields. Over millions of years, these tiny density differences grew into the galaxies, stars, and planets we see today. The cosmic microwave background provides a baby picture of the universe, showing the distribution of matter and energy when space was only 1,000th its current size. This image reveals that the early universe was remarkably smooth and uniform, with only tiny ripples that would eventually become the cosmic web of galaxies and dark matter. But as astronomers mapped the large-scale structure of the universe, they discovered something unexpected. The matter we can see, stars, gas clouds, planets, accounts for only a small fraction of the gravitational influence needed to explain galactic behavior. Galaxy rotation curves showed that stars in outer regions orbit much faster than they should if only visible matter provided the gravitational force. This led to one of the most profound discoveries in modern cosmology. Most of the universe consists of invisible dark matter that interacts gravitationally but emits no light. Computer simulations reveal that this dark matter forms a vast scaffold of filaments and nodes, the cosmic web along which normal matter flows like water, following underground channels. Here's how this hidden architecture shapes cosmic structure. Dark matter particles interact only through gravity, allowing them to begin clumping together immediately after the Big Bang without interference from electromagnetic forces. Normal matter, which does interact electromagnetically, couldn't begin forming large structures until after recombination allowed it to follow gravitational influences without being scattered by radiation. The result is a universe where dark matter provides the gravitational framework, and normal matter fills in the details. Dark matter halos surround every galaxy, providing the gravitational wells in which stars and gas can accumulate. Without this invisible scaffolding, galaxies couldn't form or maintain their structure against the expansion of space. Even more mysterious is dark energy, the force driving the accelerated expansion of the universe. In 1998, two independent teams studying distant supernovas discovered that cosmic expansion is speeding up rather than slowing down as everyone expected. Something is pushing space apart with ever-increasing strength. Dark energy makes up approximately 68% of everything that exists, yet we have no idea what it actually is. It behaves like Einstein's cosmological constant, a property of space itself that becomes stronger as space expands. The more space there is, the more dark energy there is to drive further expansion. This discovery revealed that we live in a universe dominated by components we don't understand. Normal matter, everything made of atoms, comprises only 5% of cosmic reality. Dark matter accounts for 27%. Dark energy makes up the remaining 68%. We are literally living in a cosmos where 95% of existence remains mysterious. Computer simulations using these proportions of normal matter, dark matter, and dark energy successfully reproduce the large-scale structure we observe. They show how the cosmic web forms as dark matter clumps under its own gravity, creating filaments that span hundreds of millions of light years. Normal matter flows along these filaments, accumulating at intersections to form galaxy clusters. Here's what this hidden architecture means for cosmic evolution. The universe isn't just expanding randomly, It's developing structure at multiple scales simultaneously. Dark matter creates the largest scale framework. Normal matter forms galaxies and stars within this framework. Stellar processes create heavy elements and planetary systems. Chemistry enables the complexity necessary for life. Each level of organization depends on the levels below it, creating a cosmic hierarchy that stretches from quantum particles to galaxy clusters. The same gravitational forces that curve space-time around massive objects also guide the flow of matter along dark matter filaments, ensuring that structure continues forming despite cosmic expansion. The cosmic microwave background provides precise measurements of the parameters governing this evolution. The universe has a flat geometry, meaning space extends infinitely in all directions without curving back on itself. The age of the universe is 13.8 billion years. The rate of current expansion, the Hubble constant, is 70 kilometers per second per megaparsec. These numbers encode the entire history and future of cosmic evolution. They determine how long stars will continue forming, when galaxy mergers will cease, and ultimately, when the universe will enter its final era of expansion into cold, empty space. The architecture revealed by Einstein's equations and confirmed by astronomical observations shows us living in a cosmos with a definite beginning, a complex present, and a predictable future. But this architectural understanding raises new questions about the fundamental nature of reality. Why does space-time have the properties it does? Why do the fundamental constants have values that allow complex structure to form? Why does the universe appear fine-tuned for the existence of galaxies, stars, planets, and life? Some cosmologists propose that our universe is just one bubble in an infinite multiverse, where different regions have different physical laws and constants. In this view, we observe a life-friendly universe because we couldn't exist in regions where the laws of physics don't allow complexity to develop. The apparent fine-tuning is a selection effect. We necessarily find ourselves in a cosmic bubble where our existence is possible. Others suggest that the laws of physics themselves might evolve, with different cosmic epochs governed by different sets of fundamental principles. In this scenario, the universe we observe represents just one phase in an eternal cycle of cosmic birth, evolution, and transformation. Here's what we can say with confidence about the universe's hidden architecture. Space-time is dynamic, responding to matter and energy according to Einstein's field equations. The cosmos is dominated by dark matter and dark energy that we don't understand but can measure through their gravitational and expansion effects. Large-scale structure forms hierarchically, with smaller objects merging to create larger ones over cosmic time. This architecture provides the stage on which all cosmic drama unfolds. Stars form within dark matter halos, galaxies merge along dark matter filaments, planets condense from heavy elements created in stellar cores, life emerges from chemistry enabled by cosmic evolution. Intelligence develops the capacity to discover the hidden forces and invisible matter that shaped its cosmic environment. When we map the cosmic web of dark matter filaments, measure the cosmic microwave background radiation, or detect gravitational waves from colliding black holes, we're exploring the architecture of space-time itself. We're discovering the hidden framework that connects every atom in our bodies to the largest structures in the observable universe. This exploration reveals that we live in a cosmos far stranger and more beautiful than our ancestors imagined. The universe has invisible components, dynamic geometry, and evolutionary processes that operate across scales from quantum to cosmic. The space between stars isn't empty. It's filled with dark matter, dark energy, and the curved geometry of space-time itself. Understanding this hidden architecture doesn't diminish the wonder of existence, it amplifies it. We are not just arrangements of atoms in empty space. We are complex patterns of matter and energy embedded in the dynamic fabric of space-time, connected through gravity and evolution to every other structure in the cosmic web. The questions that drove Einstein to develop relativity and Hubble to measure cosmic expansion continue motivating cosmologists today. What is the true nature of dark matter and dark energy? How did the universe achieve its current architecture? What deeper principles govern the behavior of space-time itself? These questions connect us directly to the cosmic processes that shaped our existence. The curved space-time that guides planetary orbits also enabled the formation of our solar system. The dark matter halos that organize galaxy formation also provided the gravitational environment necessary for star formation and chemical evolution. The cosmic expansion that drives galaxies apart also ensures that stars have billions of years to create heavy elements and distribute them through space. We exist within this hidden architecture, shaped by its forces and processes, capable of discovering its properties and wondering about its ultimate nature. The universe has spent 13.8 billion years creating structures complex enough to comprehend the invisible framework that gave them birth. In understanding cosmic architecture, we are glimpsing the deepest patterns underlying all existence. Close your eyes and imagine trying to understand the ocean while standing on the shore, limited to observing only the narrow band of visible light reflected from its surface. This was humanity's situation for most of our history. When we gazed upward at the cosmos, we could see stars, planets, and the faint glow of the Milky Way, but we were essentially cosmic blind to 99% of the radiation flowing through space. The transformation of human perception began in the 1600s, when Dutch lens makers discovered that carefully shaped pieces of glass could bend light to magnify distant objects. Galileo heard rumors of this spyglass and immediately grasped its potential for exploring the heavens. In 1609, he became the first person to systematically point a telescope at celestial objects, instantly expanding human vision beyond its biological limits. What Galileo saw through his primitive telescope shattered 2,000 years of assumptions about cosmic reality. The moon's surface was scarred with craters and mountains, rather than being a perfect celestial sphere. Jupiter had 4 moons orbiting around it, proving that Earth wasn't the only center of motion in the universe. Venus showed phases like our moon, confirming that it orbited the Sun rather than Earth. Here's what made these observations so revolutionary. For the first time in human history, we had extended our senses beyond their natural capabilities to perceive cosmic phenomena directly. The telescope didn't just magnify distant objects, it revealed that the universe contained structures and processes invisible to naked eye observation. Technology had become a bridge between human consciousness and cosmic reality. This principle of technological sense extension would drive every subsequent breakthrough in astronomical understanding. Just as the telescope revealed previously invisible details of planets and stars, each new instrument would unveil hidden aspects of cosmic reality, gradually building a complete picture of how the universe actually works. The next major expansion of cosmic vision came in the 1800s, when scientists discovered that white light contains all the colors of the rainbow, and that hot objects emit different wavelengths depending on their temperature and composition. By analyzing starlight through prisms, astronomers could determine what stars were made of without ever visiting them. Spectroscopy revealed that the same elements found on Earth exist throughout the universe. The hydrogen lines in the spectrum of Sirius matched exactly the hydrogen lines produced in laboratory experiments. Iron in the Sun's atmosphere absorbed the same wavelengths as iron heated in terrestrial furnaces. The cosmic and terrestrial realms operated according to the same physical laws and contained the same basic ingredients. But spectroscopy revealed something even more profound. In 1912, Vesto Slipher discovered that the spectral lines from distant galaxies were shifted toward longer, redder wavelengths. This redshift indicated that the galaxies were moving away from Earth at tremendous speeds, the first hint that the universe itself might be expanding. Here's how this expansion reveals itself through the behavior of light. When a source of waves moves away from an observer, the waves get stretched to longer wavelengths. Police use this Doppler effect to measure car speeds with radar. Astronomers use it to measure the speeds of stars and galaxies with light. The redshift of distant galaxies told us that space itself was carrying them away from us at speeds reaching thousands of kilometers per second. The early 20th century brought another revolutionary expansion of cosmic vision. Radio astronomy began accidentally in 1931, when Carl Jansky, investigating static that interfered with transatlantic radio communications, discovered that some of the noise came from the center of our galaxy. Space, it turned out, was filled with radio waves generated by cosmic phenomena. Radio telescopes revealed a universe invisible to optical observation. They detected radiation from hydrogen gas in interstellar space, mapping the spiral structure of our galaxy. They discovered quasars, extraordinarily luminous objects powered by supermassive black holes billions of light-years away. They found pulsars rapidly spinning neutron stars that sweep beams of radiation across space like cosmic lighthouses. Most importantly, radio astronomy led to the discovery of the cosmic microwave background radiation in 1965. This faint signal, present in every direction astronomers looked, carried the information about the state of the universe when it was only 380,000 years old. For the first time, humans could observe the universe as it existed in its infancy. Here's what this ancient radiation reveals about cosmic history. The temperature variations in the cosmic microwave background differences of only a few millionths of a degree show the density fluctuations that would eventually grow into galaxies and galaxy clusters. By mapping these tiny temperature differences across the entire sky, astronomers created a baby picture of the universe showing the seeds of all future cosmic structure. The launch of space-based telescopes in the latter half of the 20th century removed the final barrier, limiting human cosmic vision Earth's atmosphere. Our planet's atmospheric shield protects us from harmful radiation, but also blocks most wavelengths of light from reaching ground-based telescopes. Only narrow windows of visible light and radio waves can penetrate to Earth's surface. The Hubble Space Telescope, launched in 1990, extended human vision across the entire history of the observable universe. Its images revealed galaxies forming when the cosmos was less than 1 billion years old, showed the birth and death of stars in unprecedented detail, and provided the observations that led to discovering dark energy's acceleration of cosmic expansion. X-ray telescopes revealed the violent, high-energy universe, hidden from optical observation. They detected the million-degree gas surrounding galaxy clusters, the accretion disks of matter spiraling into black holes, and the shock waves generated by stellar explosions. Infrared telescopes peered through cosmic dust to witness star formation in regions where optical light cannot penetrate. Ultraviolet telescopes observed the hot surfaces of young massive stars and the tenuous gas between galaxies. Gamma-ray detectors captured the most energetic explosions in the universe, gamma-ray, bursts that release more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. Here's what this multi-wavelength approach revealed about cosmic reality. Every astronomical object emits radiation across the entire electromagnetic spectrum, but different physical processes dominate at different wavelengths. To understand how stars, galaxies, and other cosmic structures actually work, astronomers need to observe them in all types of light simultaneously. A supernova explosion illustrates this principle perfectly. In visible light, we see the expanding shell of hot gas ejected from the dying star. In X-rays, we observe the shock wave heating surrounding material to millions of degrees. In radio waves, we detect the interaction between the expanding debris and the magnetic fields of interstellar space. In gamma rays, we witness the nuclear reactions creating elements heavier than iron. No single wavelength tells the complete story. The 21st century has brought even more revolutionary expansions of cosmic vision. Gravitational wave detectors achieved the seemingly impossible feat of measuring distortions in space-time itself. When massive objects like black holes spiral together and merge, They create ripples in the fabric of space-time that propagate outward at the speed of light. These gravitational waves carry information about cosmic events that produce no light whatsoever. The collision of two black holes generates gravitational waves, but no electromagnetic radiation, because black holes trap light within their event horizons. Gravitational wave astronomy opened a completely new sensory channel for exploring the universe. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, measures gravitational waves by detecting changes in the length of laser beams that are smaller than 1/10,000th the width of a proton. This represents the most precise measurement ever achieved by human technology, equivalent to measuring the distance to the nearest star to an accuracy smaller than an atomic nucleus. Here's what gravitational wave detection reveals about cosmic extremes. The black hole mergers observed by LIGO involve objects 20 to 60 times more massive than our Sun, colliding at speeds approaching half the speed of light. In the final fraction of a second before merger, these black holes orbit each other hundreds of times per second, radiating away more energy in gravitational waves than all the stars in the observable universe emit in light. Neutrino astronomy provides another window into cosmic processes, invisible to electromagnetic observation. Neutrinos are ghostly particles that barely interact with normal matter. Trillions of them pass through your body every second without any detectable effect. But this very property that makes them nearly invisible also allows them to escape from the cores of stars and supernovas, carrying direct information about nuclear processes occurring in cosmic furnaces. Neutrino detectors built in underground laboratories detect these cosmic messengers using tanks containing thousands of tons of ultra-pure water or other materials. When a high-energy neutrino occasionally collides with an atomic nucleus, it produces a brief flash of light that sensitive instruments can record. Each detected neutrino provides a direct probe of nuclear reactions occurring inside distant stars or in the aftermath of stellar explosions. The most ambitious extension of human cosmic vision now under development involves particle accelerators that recreate conditions from the first moments after the Big Bang. The Large Hadron Collider can accelerate protons to energies equivalent to those that existed when the universe was only 1/1,000,000th of a second old, allowing physicists to study the fundamental particles and forces that shaped cosmic evolution. Here's what these high-energy experiments reveal about cosmic origins. The same particles and interactions that governed the behavior of matter in the primordial universe continue operating today, but at much lower energies. By recreating early universe conditions in the laboratory, physicists can test theories about cosmic inflation, dark matter, and the unification of fundamental forces. Quantum computers represent the newest frontier in cosmic vision technology. These devices exploit quantum mechanical properties to process information in ways that classical computers cannot match. They may eventually solve complex astrophysical equations that currently require approximations, revealing new insights about black hole physics, cosmic structure formation, and the quantum origins of spacetime itself. Artificial intelligence and machine learning algorithms are already transforming how we process the vast quantities of data generated by modern telescopes and detectors. These systems can identify patterns in cosmic phenomena that would take human astronomers decades to recognize, accelerating the pace of discovery and revealing subtle relationships between different types of cosmic objects. The James Webb Space Telescope represents the current pinnacle of space-based observation, designed to observe the universe in infrared light with unprecedented sensitivity and resolution. Its mirrors, kept at temperatures just above absolute zero, can detect the heat radiation from the first galaxies that formed after the cosmic dark age ended 400 million years after the Big Bang. Here's what future expansions of cosmic vision might reveal. Space-based gravitational wave detectors will observe black hole mergers across the entire observable universe, potentially detecting the signatures of cosmic inflation in gravitational waves from the Big Bang itself. Extremely large ground-based telescopes will directly image the atmospheres of planets orbiting nearby stars, searching for chemical signatures of biological activity. Neutrino detectors of unprecedented size may detect the background of relic neutrinos left over from the Big Bang, providing another direct probe of cosmic origins. Radio telescope arrays spread across multiple continents will create virtual instruments with resolution sharp enough to image the event horizons of black holes in distant galaxies. The expansion of human cosmic vision from Galileo's first telescope to gravitational wave detectors represents one of the most remarkable achievements in the history of consciousness. We have extended our senses across the entire electromagnetic spectrum and beyond, developing the ability to perceive gravitational waves, neutrinos, and the quantum properties of matter and energy. This technological evolution mirrors the biological evolution that created our sensory organs in the first place. Eyes evolved to detect electromagnetic radiation in the narrow band we call visible light. Ears evolved to detect pressure waves in air that we call sound. Our technological instruments have evolved to detect every form of radiation and particle that carries information through space. Here's the profound implication of this sensory expansion. We are no longer limited to perceiving only the tiny fraction of cosmic reality accessible to biological senses. We can observe the universe as it actually is, a vast arena of physical processes operating across scales from quantum to cosmic, involving forms of matter and energy that biological evolution never equipped us to detect directly. Each expansion of cosmic vision has revealed that the universe is stranger, more violent, more beautiful, and more comprehensible than previous generations imagined. Radio astronomy showed us a cosmos filled with invisible radiation. X-ray astronomy revealed black holes and neutron stars. Gravitational wave astronomy opened our ears to the vibrations of space-time itself. The questions that drive these technological developments connect directly to humanity's deepest curiosities about existence. What is the universe made of? How did it begin? How will it end? Are we alone? Each new instrument and detection technique represents another step toward answering these fundamental questions about our place in cosmic reality. We exist at a unique moment in the history of consciousness. The first time that matter organized into biological form has developed the technological capability to perceive the full spectrum of cosmic phenomena. Through our instruments, the universe has gained the ability to observe and understand itself across all scales of space and time. The cosmic vision we've developed reveals that we are not passive observers of distant phenomena. We are active participants in the ongoing cosmic story, using the products of stellar evolution, the heavy elements in our brains, and instruments to comprehend the processes that created us. Our expanding cosmic vision represents the universe awakening to its own nature and history. Imagine an object so dense that a teaspoon of its material would weigh 6 billion tons more than all the cars, trucks, and buses on Earth combined. Picture a region of space where gravity becomes so intense that time itself slows to a crawl, and where space curves so dramatically that it closes in on itself, trapping even light forever. These aren't science fiction fantasies, they're the cosmic extremes that actually exist in our universe, pushing the laws of physics to their absolute limits. Black holes represent the ultimate cosmic extreme, places where Einstein's equations predict that space-time itself breaks down completely. When a star at least 25 times more massive than our Sun exhausts its nuclear fuel, nothing can prevent gravitational collapse. The core contracts from the size of Earth to a point of infinite density in less than 1 second, creating what physicists call a singularity, a place where the known laws of physics simply stop working. Here's what happens during this catastrophic collapse. As the stellar core shrinks, its escape velocity, the speed needed for anything to break free from its gravitational pull, approaches the speed of light. When the core becomes smaller than its Schwarzschild radius, the escape velocity exceeds light speed. Since nothing can travel faster than light, nothing can escape. The black hole's event horizon forms a one-way boundary surrounding a region of spacetime cut off from the rest of the universe. The physics of black holes challenges every intuition we have about reality. Time doesn't flow at the same rate everywhere around a black hole. An astronaut falling toward the event horizon would experience time normally, but distant observers would see the astronaut's clock running slower and slower as gravity's grip intensifies. At the event horizon itself, time appears to stop completely from the outside perspective. Space becomes equally warped near black holes. The distance between any 2 points depends on the path you take to measure it. Straight lines curve back on themselves. The normal geometry of flat space where parallel lines never meet and the angles of triangles add up to 180 degrees breaks down completely. But black holes aren't just cosmic vacuum cleaners sucking up everything around them. They're extraordinarily selective about what they capture. Only objects that venture within the event horizon get trapped permanently. Material orbiting outside this boundary can circle a black hole indefinitely, like planets orbiting a star, as long as it maintains sufficient orbital velocity. The supermassive black hole at the center of our galaxy, called Sagittarius A star, contains 4 million times the mass of our Sun compressed into a region smaller than our solar system. Radio telescopes can track individual stars orbiting this invisible monster, watching them accelerate to speeds exceeding 5,000 kilometers per second as they swing around their closest approach. Here's what these stellar orbits reveal about the nature of black holes. The stars follow precise elliptical paths, predicted by Einstein's general relativity, confirming that black holes behave exactly as the equations suggest. During their closest approaches, the stars experience gravitational redshift. Their light gets stretched to longer wavelengths as it climbs out of the black hole's gravitational well. Even more extreme are the supermassive black holes powering quasars, the most luminous objects in the observable universe. These cosmic monsters contain billions of solar masses and generate more energy than entire galaxies by converting the gravitational potential energy of infalling matter into radiation. Material spiraling into these black holes heats to temperatures exceeding 1 billion degrees Celsius, glowing brilliantly across the entire electromagnetic spectrum. The accretion disks surrounding supermassive black holes operate like cosmic particle accelerators, launching jets of plasma at speeds approaching 99% the speed of light. These relativistic jets can extend for millions of light years, carrying energy and magnetic fields far beyond the host galaxy. Some quasar jets are so powerful they can be observed across billions of light years of cosmic distance. Neutron stars represent another form of cosmic extreme matter, compressed to densities that exist nowhere else in the universe. When a star between 8 and 25 times the mass of our Sun exhausts its nuclear fuel, the core collapses until protons and electrons get crushed together to form neutrons. The result is an object containing more mass than our Sun, compressed into a sphere just 20 kilometers across. Here's what matter becomes under these extreme conditions. The density of a neutron star is approximately 1 billion tons per cubic centimeter, so dense that all of humanity could be compressed into a volume smaller than a sugar cube. At these densities, atomic nuclei get crushed together, creating a form of matter that doesn't exist naturally anywhere on Earth. Neutron stars can spin at rates that seem impossible for objects so massive. The fastest spinning neutron star yet discovered rotates 716 times per second. At this rate, the surface of the neutron star moves at approximately 1/4 the speed of light. The centrifugal forces trying to tear the star apart are balanced only by gravitational forces stronger than anything else in the universe except black holes. The magnetic fields of neutron stars exceed Earth's magnetic field by factors of trillions. These intense magnetic fields accelerate charged particles to tremendous energies, creating beams of radiation that sweep across space like lighthouse beams. When these beams point toward Earth, we observe pulsars, neutron stars that appear to flash on and off with clockwork precision. The most precise clocks in the universe are actually spinning neutron stars. Some pulsars maintain their rotation period stable to better than 1 part in a million billion, making them more accurate timekeepers than atomic clocks on Earth. Astronomers use these cosmic chronometers to test Einstein's theory of relativity and search for gravitational waves from cosmic collisions. Dark matter represents a different kind of cosmic extreme matter that interacts gravitationally but remains completely invisible to electromagnetic observation. This mysterious substance comprises 27% of everything in the universe, yet it produces no light, absorbs no light, and reflects no light. We know it exists only through its gravitational influence on visible matter. Here's what dark matter does to cosmic structure. Computer simulations show that without dark matter, galaxies couldn't form or maintain their structure against the expansion of space. The visible matter we observe, stars, gas clouds, planets, represents only the foam on top of a vast ocean of invisible dark matter that provides the gravitational scaffolding for all cosmic architecture. Galaxy rotation curves provide the clearest evidence for dark matter's existence. Stars in the outer regions of galaxies orbit much faster than they should, if only visible matter provided the gravitational force holding them in orbit. These stars should either fly away into space or spiral inward toward the galactic center. Instead, they maintain stable orbits because they're embedded in massive halos of dark matter. Dark matter particles are streaming through your body right now. Trillions of them pass through every square centimeter of Earth every second, but they interact so weakly with normal matter that they pass through the entire planet without any detectable effect. Building detectors sensitive enough to catch even one dark matter particle requires underground laboratories shielded from cosmic rays and equipped with the most sensitive instruments human technology can create. The search for dark matter has led to some of the most sophisticated experiments ever attempted. Deep underground mines, house tanks containing hundreds of tons of ultra-pure materials, cooled to temperatures just above absolute zero, and surrounded by layers of shielding to block every form of background radiation. These detectors wait patiently for the extremely rare event when a dark matter particle might collide with an atomic nucleus and produce a detectable signal. Dark energy represents an even more mysterious cosmic extreme. This invisible force comprises 68% of the universe and drives the accelerated expansion of space itself. Unlike dark matter, which clumps together gravitationally to form cosmic structure, dark energy appears uniform throughout space and grows stronger as the universe expands. Here's what dark energy means for the future of the cosmos. As space continues expanding, the density of normal matter and dark matter decreases the same amount of per material gets spread over larger volumes. But dark energy behaves differently. Its density remains constant as space expands, meaning the total amount of dark energy in the universe increases as space itself increases. This leads to a cosmic tug-of-war between gravity trying to slow expansion and dark energy trying to accelerate it. For the first 7 billion years of cosmic history, gravity dominated and expansion gradually slowed. Then dark energy took control, and expansion began accelerating. This acceleration will continue indefinitely, eventually carrying distant galaxies beyond the reach of our most powerful telescopes. The discovery of dark energy's acceleration came from observations of distant supernovas, stellar explosions so bright they can be seen across billions of light-years. Type Ia supernovas occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and explode with remarkably consistent brightness. This makes them cosmic standard candles that astronomers can use to measure distances across the universe. When 2 independent teams measured the distances and recession velocities of dozens of these distant supernovas in 1998, they expected to find that cosmic expansion was slowing down due to gravity's influence. Instead, they discovered that expansion was speeding up. The universe wasn't just expanding, it was accelerating its expansion at an increasing rate. This discovery revealed that we live in a cosmos dominated by forms of matter and energy we don't understand. Normal matter, everything made of atoms, comprises only 5% of cosmic reality. Dark matter accounts for 27%. Dark energy makes up the remaining 68%. We are literally living in a universe where 95% of existence remains mysterious. The extreme objects and phenomena we've discovered challenge the limits of human comprehension. Black holes where time stops, and space curves infinitely. Neutron stars spinning hundreds of times per second with magnetic fields trillions of times stronger than Earth's. Dark matter that outweighs visible matter 5 to 1, yet remains completely invisible. Dark energy that will ultimately determine the fate of cosmic expansion. Here's what these extremes reveal about the nature of reality. The universe operates according to physical laws that remain valid even under the most extreme conditions imaginable. Einstein's equations correctly predict the behavior of black holes containing billions of solar masses. The same nuclear physics that explains how stars shine also explains how neutron stars can exist. Quantum mechanics governs both the smallest particles and the largest cosmic structures. The search for cosmic extremes continues, pushing the boundaries of technology and theory. Gravitational wave detectors can now observe black hole mergers occurring billions of light-years away, measuring space-time distortions smaller than a proton width. Radio telescope arrays are creating images of black hole event horizons, allowing us to see the edge of cosmic extremes for the first time. Future space-based gravitational wave detectors will observe cosmic collisions across the entire observable universe, potentially detecting the merger of supermassive black holes when galaxies collide. Advanced particle accelerators may create conditions extreme enough to produce dark matter particles in laboratory settings, finally revealing the nature of the invisible matter that dominates cosmic structure. The cosmic extremes we've discovered aren't just exotic curiosities existing in distant regions of space. They're fundamental components of the universe that shaped cosmic evolution and continue influencing the development of galaxies, stars, and planetary systems. The supermassive black holes at galactic centers regulate star formation throughout their host galaxies. Neutron star mergers create and distribute the heaviest elements in the periodic table. Dark matter provides the gravitational framework that allows cosmic structure to exist. We exist in a universe of extremes that exceed anything our biological evolution prepared us to comprehend. Yet through careful observation and mathematical analysis, we've learned to understand these phenomena and incorporate them into our picture of cosmic reality. The same universe that created black holes and neutron stars also created brains capable of discovering and studying these cosmic extremes. This represents one of the most remarkable achievements in the history of consciousness. Matter organized into biological form has developed the conceptual and technological tools necessary to comprehend cosmic phenomena that operate at scales and intensities completely beyond direct human experience. We can now study objects so dense that atoms get crushed out of existence, forces so strong they accelerate space-time itself, and particles so elusive they rarely interact with anything else in the universe. The questions that drive our search for cosmic extremes connect directly to fundamental mysteries about the nature of existence. What happens to information that falls into a black hole? How do the quantum properties of matter behave under extreme gravitational fields? What is the true nature of dark matter and dark energy? How will cosmic extremes shape the ultimate fate of the universe? These questions push us toward the deepest possible understanding of physical reality. In studying cosmic extremes, we're exploring the absolute limits of what's possible within the laws of physics. We're discovering how matter, energy, space, and time behave when pushed to their breaking points. The cosmic extremes we've found reveal that we live in a universe far stranger and more wonderful than our ancestors could have imagined. Reality includes regions where the normal rules of physics break down, forms of matter that exist nowhere on Earth, and invisible forces that shape the destiny of cosmic evolution. Understanding these extremes doesn't diminish the wonder of existence, it amplifies it, revealing that we inhabit a cosmos of infinite mystery and boundless possibility. Every cosmic discovery we've made reveals 10 new mysteries that push human understanding toward even deeper questions about the nature of reality itself. We stand at the edge of knowledge, peering into fundamental puzzles that may require entirely new forms of science to resolve. These aren't just academic questions, they're the growing edge of human consciousness reaching toward mysteries that could reshape our understanding of existence. The multiverse hypothesis suggests that our universe might be just one bubble in an infinite cosmic foam, where different regions of space-time operate under completely different physical laws. This possibility emerged from our best theories about cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. Here's what cosmic inflation reveals about the possible nature of reality. If space can expand faster than light during inflation, and if this process can begin in one region while continuing in others, then inflation might create an endless succession of universe bubbles. Each bubble would expand and cool into a separate cosmic realm, with its own set of physical constants and laws. In some universe bubbles, gravity might be stronger or weaker than in ours. In others, the electromagnetic force might have different strength, preventing atoms from forming stable bonds. Some bubbles might have more or fewer spatial dimensions than our familiar three. Others might experience time flowing in different directions or at different rates. This multiverse scenario makes testable predictions. If our universe is one bubble in an infinite foam, we might occasionally collide with neighboring bubbles, leaving detectable signatures in the cosmic microwave background radiation. Searches for these collision signatures are already underway, looking for circular patterns in the ancient light that would indicate contact with other cosmic realms. But the multiverse raises profound questions about the nature of scientific explanation. If anything that can happen does happen somewhere in the multiverse, then the apparent fine-tuning of our universe becomes inevitable rather than requiring special explanation. We observe a cosmos with properties that allow complexity and life, because we couldn't exist in bubble universes where such properties don't exist. Quantum mechanics reveals that reality at its most fundamental level operates through probability and uncertainty, rather than the deterministic clockwork that classical physics predicted. When we measure the position of a particle, we fundamentally disturb its momentum. When we observe which path a photon takes through a double-slit experiment, we change the nature of the experiment itself. Here's where quantum mechanics becomes cosmically relevant. The tiny density fluctuations that grew into galaxies and galaxy clusters originated as quantum uncertainty in the inflating universe. The same indeterminacy that prevents us from knowing both the position and momentum of an electron simultaneously created the cosmic web of dark matter filaments, along which all large-scale structure formed. Quantum entanglement presents an even deeper puzzle about the nature of space and time. When two particles become entangled, measuring the properties of one instantly affects the properties of the other, regardless of the distance separating them. This spooky action at a distance suggests that space and time might not be fundamental features of reality, but rather emergent properties arising from more basic quantum relationships. The holographic principle proposes that all the information contained within a volume of space can be encoded on its two-dimensional boundary. This idea emerged from studies of black hole physics, where the entropy of a black hole depends on the area of its event horizon rather than its three-dimensional volume. If the holographic principle applies to the entire universe, then our three-dimensional experience of reality might be a projection from information stored on a distant two-dimensional surface. General relativity describes space-time as a curved continuum that responds dynamically to matter and energy, while quantum mechanics treats space and time as fixed backgrounds on which quantum fields fluctuate. These two theories work perfectly in their respective domains, but cannot yet be unified into a single description of cosmic reality. String theory proposes that all particles and forces emerge from tiny vibrating loops existing in 11 dimensions, most of which remain hidden from direct observation. Different vibration modes of these fundamental strings correspond to different particles. Electrons, photons, quarks, and all the rest arise from the same basic stringy constituents oscillating in different patterns. Here's what string theory suggests about the deepest level of reality. The particles we observe aren't fundamental building blocks, but rather different musical notes played by vibrating strings. The forces that govern cosmic evolution, gravity, electromagnetism, and the nuclear forces represent different harmonies in this cosmic symphony of string vibrations. String theory requires extra spatial dimensions beyond the three we experience directly. These additional dimensions might be compactified, curled up so small that we can't detect them with current technology. The way these extra dimensions curl determines which particles and forces exist in our observable three-dimensional slice of reality. Loop quantum gravity offers an alternative approach to unifying relativity and quantum mechanics by proposing that space-time itself has a granular structure at the smallest possible scales. Rather than being infinitely divisible, space and time might consist of discrete units, quantum pixels, that form the fabric of reality at distances smaller than anything we can currently measure. This quantum geometry suggests that black hole singularities might not be points of infinite density, but rather regions where space-time undergoes quantum transitions into new geometric configurations. The Big Bang itself might represent a quantum bounce rather than a moment of creation, from nothing, a transition from a previous cosmic epoch that contracted until quantum effects reversed the collapse into expansion. The search for extraterrestrial life combines cosmic chemistry with planetary science, revealing that the elements necessary for life exist throughout the universe. While potentially habitable planets orbit stars in every direction we look, water, carbon, oxygen, nitrogen, phosphorus, and sulfur, the chemical building blocks of terrestrial biology, form naturally in stellar cores and get distributed through space by stellar winds and supernova explosions. Exoplanet discoveries have revealed that planetary systems are common throughout our galaxy. Thousands of confirmed planets orbit other stars, ranging from massive gas giants orbiting closer to their stars than Mercury orbits our Sun, to rocky worlds in the habitable zones where liquid water could exist on planetary surfaces. Here's what astrobiology teaches us about the cosmic context for life. The same nuclear processes that create heavy elements in stellar cores also provide the chemical diversity necessary for complex chemistry. The same gravitational processes that form planetary systems also create the stable orbital environments where chemistry can evolve into biology over billions of years. The discovery of extremophile organisms on Earth, life forms that thrive in boiling water, highly acidic environments, intense radiation, and other conditions that would quickly kill most life forms, has expanded our understanding of where biology might be possible throughout the universe. Life appears far more adaptable and resilient than earlier generations of scientists assumed. Artificial intelligence and quantum computers are beginning to process cosmic data in ways that exceed human cognitive capabilities, potentially revealing patterns and relationships that biological brains cannot detect. Machine learning algorithms can already identify galaxy types, classify stellar spectra, and detect gravitational wave signals buried in instrumental noise with accuracy exceeding human experts. Quantum computers exploit quantum mechanical properties like superposition and entanglement to perform certain calculations exponentially faster than classical computers. These devices might eventually solve complex astrophysical equations that currently require approximations, revealing new insights about black hole physics, cosmic structure formation, and the quantum origins of space-time itself. Here's how artificial intelligence might transform cosmological understanding. AI systems can analyze vast datasets simultaneously, identifying subtle correlations between different types of cosmic phenomena that human researchers might take decades to recognize. They can simulate cosmic evolution with unprecedented detail, testing theoretical predictions against observational data in ways that exceed current computational capabilities. The combination of AI and quantum computing might enable us to model the universe from quantum scales to cosmic scales simultaneously, revealing how the behavior of fundamental particles influences the formation of galaxies and vice versa. This could lead to breakthrough insights about the connections between quantum mechanics and general relativity. The questions that keep us awake at night about cosmology represent the growing edge of human consciousness, reaching toward mysteries that may require entirely new forms of intelligence to comprehend. Why does anything exist at all rather than nothing? What came before the Big Bang? Are the laws of physics universal, or do they vary across cosmic regions? Is consciousness a fundamental feature of reality, or an emergent property of complex information processing? These questions push us toward the deepest possible understanding of existence itself. They challenge not just our scientific theories, but our basic concepts of causation, explanation, and the relationship between mind and matter. Answering them might require forms of intelligence that combine human intuition with artificial reasoning and quantum computational power. The mystery of consciousness itself poses particularly profound challenges for cosmological understanding. How does the universe create structures complex enough to contemplate their own existence? Is consciousness reducible to information processing, or does it require something beyond physical matter and energy? Could consciousness be a fundamental feature of reality that influences cosmic evolution in ways we haven't yet recognized? Some theorists propose that consciousness might be connected to quantum mechanics through microtubules in brain cells that maintain quantum coherence even at biological temperatures. Others suggest that consciousness emerges from the integration of information processing across neural networks. Still others propose that consciousness represents a fundamental aspect of reality that exists at all scales from quantum to cosmic. The anthropic principle raises questions about whether the universe's properties are fine-tuned for the existence of complexity and life. The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, have values that allow atoms to form, stars to shine, and chemistry to create complex molecules. If any of these constants were significantly different, the universe might contain only simple particles with no possibility for structure or complexity. Here's what this apparent fine-tuning might mean for cosmic understanding. Either the fundamental constants are determined by some deeper physical principle we haven't yet discovered, or our universe is one of countless cosmic realms with different constants, and we necessarily observe values that allow our existence. Both possibilities have profound implications for the nature of physical law and cosmic evolution. The ultimate fate of the universe depends on the balance between gravity and dark energy. Current observations suggest that dark energy will continue driving accelerated expansion indefinitely, eventually carrying distant galaxies beyond the reach of observation and leaving our local cluster of galaxies isolated in an increasingly empty space. In the far future, stars will exhaust their nuclear fuel and fade to cold white dwarfs, neutron stars, and black holes. Even these compact objects will eventually evaporate through Hawking radiation, leaving only elementary particles scattered through ever-expanding space. This heat-death scenario represents the ultimate triumph of entropy over order, but quantum mechanics suggests that even this cosmic ending might not be final. Quantum fluctuations could eventually create new inflationary regions that spawn fresh universes. Virtual particles popping into existence from vacuum energy might occasionally create matter-antimatter pairs that don't immediately annihilate. Given enough time periods so vast they exceed human comprehension, quantum uncertainty might resurrect cosmic evolution. The questions driving cosmological research today will likely seem quaint to future forms of intelligence equipped with quantum computers, AI reasoning systems, and detection technologies we can't yet imagine. But these questions establish the trajectory along which cosmic understanding will continue evolving. Each generation of cosmic investigators builds on the insights of their predecessors while developing new tools and concepts that reveal previously hidden aspects of reality. The questions that challenge us today about dark matter, dark energy, quantum gravity, and the multiverse are preparing the foundation for discoveries that will reshape cosmic understanding in ways we can't currently anticipate. Here's what we can predict about the future of cosmological questioning. Each answer we discover will reveal new layers of cosmic mystery. Understanding dark matter will lead to questions about its quantum properties and cosmic role. Detecting gravitational waves from cosmic inflation will raise new questions about the physics of the Big Bang. Finding life elsewhere in the universe will pose new questions about the relationship between cosmic evolution and biological complexity. The questions that keep us awake at night about cosmology are the growing edge of consciousness encountering the deepest mysteries of existence. They represent the universe, developing the capacity to question its own nature and origins through biological and artificial intelligence. In asking these questions, we're participating in cosmic evolution's ongoing journey toward greater complexity and understanding. The cosmic story that began with the Big Bang and led through stellar nucleosynthesis, galaxy formation, and biological evolution to the emergence of consciousness, capable of contemplating its own origins, continues unfolding through our questions about the ultimate nature of reality. The mysteries that challenge us today are preparing the way for forms of understanding that transcend our current ability to imagine. We stand at a remarkable moment in the history of existence, the first time that matter organized into biological form has developed the technological and conceptual capabilities to comprehend cosmic phenomena across all scales of space and time. The universe has spent 13.8 billion years creating the conditions necessary for part of itself to become conscious of its own nature and history. Every atom in your body participated in this cosmic story. The hydrogen in your DNA dates back to the first 3 minutes after the Big Bang, when nuclear fusion created the light elements that still fuel stellar fires today. The carbon in your cells formed inside dying stars through helium fusion, then got distributed through space when those stars exhausted their nuclear fuel and expelled their outer layers. The oxygen you breathe emerged from massive stars that fused silicon into heavier elements during their final moments of life. The calcium in your bones was created when these massive stars captured additional neutrons and protons in the intense heat and pressure of supernova explosions. The iron in your blood was forged in the cores of stellar furnaces, operating at temperatures exceeding 100 million degrees Celsius. Here's what this cosmic heritage means for human existence. You are not just made of star stuff, you are star stuff that has learned to contemplate its own stellar origins. The same nuclear processes that power the sun also enable the chemistry that makes consciousness possible. The same gravitational forces that organize galaxies also shaped the planetary environment where biological evolution could unfold. This connection between cosmic processes and human awareness runs deeper than simple chemical composition. The neural networks that generate thoughts and emotions operate according to the same physical laws that govern stellar fusion and galactic rotation. The electromagnetic forces that bind atoms into molecules also enable the flow of electrical signals through synapses in your brain. When you wonder about the nature of reality, you're participating in the universe's ongoing evolution toward greater complexity and understanding. The questions that arise in human consciousness represent cosmic matter, organizing itself into patterns capable of investigating cosmic matter. We are the universe developing the capacity to study itself through biological intelligence. Our persistent curiosity about cosmology represents not just an intellectual pursuit, but a fundamental drive encoded in the neural networks that evolved to help our ancestors navigate and survive in complex environments. The same pattern recognition capabilities that enabled early humans to track animal movements and predict seasonal changes now allow us to detect exoplanets and map the cosmic web of dark matter. The tools we create to explore cosmic phenomena, from telescopes to particle accelerators to quantum computers, represent natural extensions of the sensory and cognitive capabilities that biological evolution produced over billions of years. Each technological breakthrough extends human perception beyond its biological limits, revealing previously hidden aspects of cosmic reality. Here's how our cosmic exploration connects to the deepest principles of existence. The universe operates according to discoverable mathematical laws that remain consistent across scales from quantum to cosmic. The same equations that describe electron behavior in atoms also predict the dynamics of galaxy clusters containing trillions of stars. This mathematical unity suggests that consciousness and cosmos are intimately connected through the logical structure of physical law. The fact that we can comprehend cosmic phenomena at all indicates something profound about the relationship between mind and matter. Our brains, built from recycled stellar material, can understand the nuclear processes that created their constituent atoms. This suggests that intelligence and cosmic evolution are not separate phenomena, but different aspects of the same underlying creative process. 5 billion years from now, our sun will begin its transformation into a red giant star, expanding until its outer layers engulf the inner planets and Earth's surface becomes uninhabitable. The core temperature will rise high, enough to begin fusing helium into carbon and oxygen, extending our star's lifetime for another billion years before it finally sheds its outer layers and settles into retirement as a slowly cooling white dwarf. This stellar evolution that will reshape our solar system follows the same nuclear physics that governs every other star in the universe. Our sun represents one node in the vast network of stellar furnaces that have been creating and distributing heavy elements for over 13 billion years. Its eventual death will return the carbon, oxygen, and other elements it contains to interstellar space, where they might eventually become incorporated into new planetary systems. The Andromeda Galaxy approaches our Milky Way at 120 kilometers per second, promising a cosmic collision that will begin in approximately 4.5 billion years. This galactic merger will reshape both star systems as their gravitational fields interact, flinging some stars into intergalactic space while triggering massive bursts of new star formation as gas clouds collide and compress. Despite the violence of this cosmic collision, individual stars are so widely separated that direct stellar collisions will be extremely rare. Our solar system will likely survive the merger intact, though it might end up in a completely different region of the combined galaxy. The supermassive black holes at the centers of both galaxies will eventually spiral together and merge, releasing gravitational waves that will propagate across the observable universe. Here's what these cosmic futures mean for the continuation of intelligence and exploration. Long before our sun becomes a red giant or Andromeda arrives, the questions that drive human curiosity today will likely carry consciousness, whether biological, artificial, or something entirely new, toward discoveries that transcend our current ability to imagine. The exponential growth of computational capability and artificial intelligence suggests that the next few centuries might witness intelligence amplification beyond anything biological evolution has produced. Quantum computers could solve astrophysical equations that currently require approximations, revealing new insights about black hole physics, cosmic structure formation, and the quantum origins of space-time itself. Advanced AI systems might discover patterns in cosmic data that biological brains cannot detect, leading to breakthrough insights about dark matter, dark energy, and the fundamental nature of physical law. The combination of human intuition and artificial reasoning could accelerate cosmic understanding at rates that exceed the gradual pace of biological discovery. Space-based civilizations could construct instruments of unprecedented size and sensitivity, detecting gravitational waves from cosmic inflation, observing the event horizons of black holes across the observable universe, and possibly even discovering evidence for other cosmic realms beyond our universe bubble. The search for extraterrestrial intelligence might reveal that consciousness is common throughout the cosmos, with countless forms of intelligent life investigating the same fundamental questions that drive human curiosity. Contact with alien intelligence could provide new perspectives on cosmic mysteries and accelerate scientific progress through the exchange of different approaches to understanding reality. But even if intelligence remains rare in the universe, the cosmic story will continue evolving through physical processes that operate on scales far exceeding biological lifespans. Galaxy clusters will continue growing as cosmic expansion carries them farther apart. Stars will continue forming in gas-rich galaxies until the universe's supply of hydrogen is exhausted. Black holes will continue growing through accretion and merger until they dominate the mass budget of the cosmos. The ultimate fate of cosmic evolution depends on the nature of dark energy and its long-term behavior. If dark energy remains constant, the universe will continue expanding and cooling until stars exhaust their fuel and fade to black holes and elementary particles. If dark energy grows stronger, it might eventually overcome all other forces and tear apart galaxies, stars, atoms, and even space-time itself in a Big Rip scenario. Alternatively, dark energy might weaken or change sign, allowing gravity to halt cosmic expansion and reverse it into contraction. This could lead to a big crunch, where the universe collapses back to extreme density and temperature, possibly triggering a new cycle of cosmic evolution. Here's what we know with confidence about cosmic continuation. The same physical processes that have driven cosmic evolution for 13.8 billion years will continue operating according to discoverable mathematical laws. Stars will keep converting hydrogen into heavier elements. Gravity will keep organizing matter into larger structures. Evolution will keep creating more complex forms of organization wherever conditions permit. The questions that keep us awake at night about cosmology: why does anything exist at all? What came before the Big Bang? Are we alone in the universe? Connect us directly to the cosmic processes that shaped our existence. These questions emerged from neural networks built by evolution to detect patterns and make predictions about environmental challenges and opportunities. Our cosmic curiosity represents the universe, developing new capabilities for self-understanding through the evolution of intelligence. Each generation of cosmic investigators builds on previous insights, while developing new tools and concepts that reveal previously hidden aspects of reality. The technological instruments we create extend our sensory reach across the electromagnetic spectrum and beyond, allowing us to perceive gravitational waves, neutrinos, and the quantum properties of matter and energy. These tools function as prosthetic senses that reveal cosmic phenomena completely beyond biological perception. The mathematical theories we develop encode cosmic understanding in forms that transcend the limitations of individual human lifespans. Einstein's field equations continue predicting cosmic behavior decades after his death. Quantum mechanics continues, revealing new aspects of microscopic reality long after its original formulation. These conceptual tools become part of the permanent heritage of intelligence. Our cosmic story continues because each answer we discover reveals new questions that push understanding toward deeper levels of reality. Learning about stellar nucleosynthesis led to questions about dark matter and cosmic structure formation. Discovering cosmic expansion led to questions about dark energy and the multiverse. Understanding biological evolution led to questions about consciousness and the relationship between mind and matter. This pattern of expanding mystery has characterized human inquiry since our ancestors first wondered about celestial motions and proposed that natural phenomena follow discoverable patterns. Each breakthrough in cosmic understanding has revealed that the universe is stranger, more beautiful, and more comprehensible than previous generations imagined. The cosmic perspective that emerges from modern astronomy and physics reveals that we exist at the intersection of multiple cosmic stories. We participate in the chemical evolution that began when the first stars created elements heavier than hydrogen and helium. We represent products of biological evolution that transforms chemistry into self-replicating, self-organizing, and eventually self-aware systems. We embody the ongoing development of intelligence as a cosmic force capable of understanding and potentially directing natural processes. Through science and technology, we've begun influencing our immediate cosmic environment, from altering our planet's atmosphere to sending probes throughout the solar system. The questions we ask about cosmology and the instruments we build to answer them represent early stages in intelligence's cosmic role. Future forms of consciousness might develop capabilities we can't currently imagine: direct perception of quantum phenomena, communication across interstellar distances, manipulation of space-time geometry, or creation of new cosmic structures. Here's the profound implication of our position in cosmic history. We exist at the moment when the universe first becomes capable of understanding itself through the consciousness it has created. Our scientific discoveries represent the cosmos learning about its own nature and history through biological and artificial intelligence. The cosmic story that began with the Big Bang and led through stellar nucleosynthesis, galaxy formation, planetary system development, and biological evolution to the emergence of scientific civilization continues unfolding through our investigations of cosmic reality. We are both products of this cosmic evolution and agents of its continued development. The questions that arise in human consciousness about the nature of existence connect us directly to the deepest patterns underlying all cosmic phenomena. When we wonder why the universe exists rather than nothing, we're participating in the same creative process that separated the fundamental forces, lit the first stars, and enabled the chemistry necessary for life. Our cosmic story continues because the universe has created, in us, the capacity for endless questioning and discovery. Each generation of conscious beings inherits the accumulated knowledge of previous generations, while developing new tools and insights that expand the boundaries of understanding. The cosmos that gave us birth through stellar evolution and planetary formation now depends on consciousness to continue its journey toward greater complexity and awareness. We carry the cosmic story forward through our curiosity, our instruments, our theories, and our persistent questioning of everything we think we know about reality. In contemplating the universe, we complete a cosmic circle that began 13.8 billion years ago, when matter and energy first separated from the primordial unity of the Big Bang. Through consciousness, the universe has developed the capacity to investigate its own origins, understand its own evolution, and wonder about its own future. This is why the questions that keep us awake at night about cosmology matter so profoundly. They represent the growing edge of cosmic evolution itself, pushing toward forms of understanding that transcend everything intelligence has achieved so far. Our cosmic story continues because the universe has finally created part of itself, capable of telling that story and wondering what comes next.